You guys hear me all right?
Yes.
Yeah.
Yep.
And I think I'm not sharing the screen now.
You're not sharing the screen.
You're not.
Perfect. I love it when the computer does what I intend for it to do. That usually tells me that I told it to do what I wanted. All right. So I said yesterday as we finished that we would continue talking about this design for manufacturability before we move on to talking about engineering metrology or manufacturing metrology. Just a second here. All right, that's muted. So where were we yesterday when we left off? We had just finished, I think, talking about, so we had talked about chamfers versus fillets on outside edges. And I think we had talked about...
We talked about over-constraining.
Say again?
We talked about over-constraining, and I think we were just beginning to talk about pockets.
Yeah, I think we were just starting to talk about pockets here. And
yeah, we got to the point with the corner radius your tolerance is like half the length of the radius of the tool, or diameter of the tool.
Right, so whatever our tool diameter is, we want it to be smaller, or we want the half the diameter of the tool, so the radius here in this direction, to be smaller than this radius. And that's because we want the tool to be able to feed around the part. We don't want it to jam itself into the corner and stop and then move sideways. All right, so those are some pretty obvious ones. What else do you think is going to be important, especially now if we're thinking specifically about CNC machining, and let's go ahead and stick with milling for now. What are the things that are going to be especially important that we think about if we want to design for machinability? So this is not just designing for manufacturability, but now designing for machinability. What else do you think you want to think about?
Your approach angle.
Okay, I see what you mean. So that's if I'm machining this part and I need to be able to get the tool access to make it in. So if there was some other feature right next to it, then it would be maybe hard to fit the tool in there. Is that what you mean by approach angle?
Yeah, exactly what I mean.
I guess so. I don't think that doesn't really come top of mind to me, but we talked about fillets, right? And in the CAD software, there's a button that says just fillet all the adjoining surfaces. And that's really cool because you can press that button and it puts those fillets all over all the corners. And it'll do it for chamfers too. It doesn't have to be just a fillet. And then there's an option where you can blend them together. And it looks really cool on the part, right? I mean, you have to, I don't have enough mouse cable left. But to make some surfaces, you do have to blend those different radiuses together. Those blended features are very difficult to make with standard tooling. In fact, really the only way to do it in most cases is going to be to do a 3-axis machining operation, like a surfacing operation, we'll often call that, to make that 3-dimensional surface. And sometimes you need to do that. I just wanted to get an example part here. So this one was designed pretty well. Oh, wait. Yeah, the guy that designed it took this class. Maybe that's why. Trying to see.
What is it supposed to be used for?
Oh, do you guys ever watch BattleBots on TV?
Yes.
If I stick it up in this orientation and there's another one opposite it over here, and it's painted white.
Yep.
Got it? Somebody want to say what it is? Not everybody got that.
It's the WPI BattleBot.
No.
No? Oh.
No, but it is Byte Force, and Paul Venmiglia, the head of the Byte Force team, did go to WPI, and he designed this part. It's a little ear that sticks up to protect the. Maybe it sticks up. Maybe it goes up like this. Anyway, it protects the drive mechanism for the weapon on the BattleBot. In case the thing flips over, it'll stand up. It was a bad example part to show the blending thing, though, because he didn't do that because he knew that it was hard to make those surfaces that get blended together. Oftentimes, that blend is not functional and not needed and impossible to measure. And when that's the case, I don't know. If it's impossible to measure, it's impossible to make. If it's impossible to make, you have to charge a lot for it. So when you make those fancy surfaces with all the blends together like that, it can be very expensive to make, especially if you didn't need that. So I guess that's just something to keep in mind with that. If you're doing a 3-axis machining operation, your tool has to be able to see the feature from the top. If you're doing a 5-axis machining operation, you can move the part around and move the tool around. So you've got a little bit more leverage, but again, a 5-axis machining operation is going to be more expensive to set up and operate than a 3-axis operation. So keep those things in mind. What else do I want to make sure we don't miss here? Has anybody ever drilled a hole with a hand drill?
Yeah.
Yep.
Yes.
All right. I think many of you have done this. Now, if you take that drill and you put the point of the drill right up against the surface that you want to drill and you pull the trigger, what happens?
It
Oh,
walks
It's gonna
for a
walk.
little bit.
the tip of the drill moves around like this before finally it makes a hole and then starts going in.
You gotta use a punch.
Okay, so you can do stuff to make it not do this as much. But why is it that the tip of the drill wants to do that?
It hasn't, the teeth on the drill bit haven't bit into the wood yet.
Wood, steel,
Wood, metal, whatever.
ice cream, it doesn't matter what you're drilling. It happens partly because it hasn't cut into it yet. Right, you can drill a hole in ice cream, right?
Yep.
Yeah. Okay. So if you were the piece of material that's getting drilled, and you're looking up at the drill as it comes towards you, you'll see a drill tip that looks kind of like this. It's going to rotate this way, I guess. And so then there's the rest of the drill. And the tip of the drill looks like this, and there's usually some overlap between these two cutting edges. Just as an aside, at the center of the drill, what's the surface speed?
0.
What causes the cutting action to happen? Huh. It's interesting. I don't usually get a call from Haas Automation, but I just did. Anyway, I'll answer it some other time. What's the surface speed at the center? Somebody said it, I think, right?
0.
0. What causes the chip to form on the edge of the tool? It's the edge of the tool moving through the material. So it has to have velocity, right? So no cutting happens at the center of the drill. What happens to the material at the center of the drill?
It
Does it
heats
get
up.
pushed out of the way?
Yeah, it heats up and gets pushed out of the way. Now, as you come out the cutting edge here, the surface speed increases, and then it becomes, we can figure out what it is at any diameter based on the formulas that we have, right? So as we come out, but also because these tips overlap, what if you're not absolute 100% perfectly straight up and down when you push down on the drill and start spinning? One of these edges is going to be in contact, and one of the edges is going to be a little bit up in the air. The one that's in contact is going to want to push away as soon as it starts spinning, and that's what causes the tip of the drill to walk out. Would you believe that the tip of the drill wants to walk out like that even in a CNC machine tool?
Yes.
Yep.
Yeah,
Yes.
It turns out the physics that happen at the tip of the drill bit are the same whether it's a hand drill or a CNC machine. The structure of the CNC machine, for most of them that are commercially available at least, is stronger than your arm, shoulder, elbow connection. So the spindle stays pretty rigid when the drill tip tries to walk out. But the drill tip still walks out. And so it moves over a little bit. And then we keep feeding straight down. And you could easily end up with a hole that looks in cross section like that. Now, obviously, I've exaggerated the radius of that curve. What happens if it bends too much?
It's you can't do any. It's like you're putting like a bolt in it. You can't put said bolt in the curved hole.
Goes out of tolerance?
Yeah, all of those things happen. If you're drilling through a part, so if there's a top and a bottom, the hole at this end won't have the same location as the hole at this end. That's problematic if you need stuff to line up when you bolt it together. But if it bends too much, the drill breaks. How do you keep the drill from breaking?
Pilot hole.
Okay, so drill another hole first. By a pilot hole, usually the pilot hole goes all the way through. Is that what you meant?
No, I meant a center drill.
So you meant a center drill or a spot drill. So why doesn't the tip of the center drill walk out sideways?
Because of the how
that
the
center drill or that spot drill, what you're doing, if you look at the surface of the part here, is as the drill comes in, you've made a little divot. Somebody said use a punch when we were using the hand drill. It's the same function as doing a center drill. You make a little divot here so that when your drill tip comes in, even if it contacts one side before it contacts the other, it gets pushed up against the other side and it tends to go more straight. So why doesn't the center drill, the tool that we use to make that little divot, why doesn't it walk out sideways?
because of the shape of the
Smaller.
tool.
What about the shape of the tool?
It's like it's more, the center is smaller and it's like curved in.
Let's think of the physics. So here's my drill. I'll put a little tip on it. Here's my spindle up here. And I'm holding it rigidly in that spindle or in some tool holder that's attached to the spindle, right? When the edge comes in contact with the workpiece material, it makes a cutting force that's sideways that wants to make it walk out. And so what the tip of the drill deflects, right? What's the deflection depend on? You don't need to state the equation. Just tell me what are the factors in the equation.
Length and diameter.
The length, and so that's this distance. And what else?
Diameter.
The diameter of the drill. The equation actually has radius.
Would it depend on how rigid the material the drill is made out of?
The
Is?
elastic modulus of the material.
Does the elastic modulus of the material you're drilling into matter?
It will probably impact the magnitude of the force. It will definitely impact the magnitude of the force, yeah. So the force matters. So I guess, yes, it does. Because the force is in that equation. The other thing that's in that equation is I, which is the area moment of inertia of the drill. Now the drill's a complex shape, right? Every shape has its own area moment of inertia. But we could assume that the drill is a cylinder for the sake of this estimate, and it'll help us out to understand that. But if we want, anybody remember what the equation is actually? Deflection of a simply supported beam? Pretty sure D equals, anybody remember? If you need to know it, how do you find out?
Google.
Google.
You can do
It's,
Google.
I think I have it.
The machinist
have it written
handbook.
down.
In the machinery's handbook. It's in the M1800 equations presentation.
In
We're looking
The
for deflection, right?
deflection of a simply supported beam. Simply supported just means it's held at one end.
is it? No, I think that's the wrong one.
Is it cutting force by
See, I think I
times the length
remember it,
cubed?
but I'd rather look it up. Say it again.
Cutting force times the length of the drill cubed
So
over 3 times the elastic modulus times the area moment of inertia.
divided by what's it
3
divided by?
times the 3 times the elastic modulus times the area moment of inertia.
I'll buy that. And I for a cylinder equals something divided by
It's pi r squared, pi r to the 4th power over 4.
pi r to the 4th over 4. Both those equations look good to me. I think those are correct.
Or would it be?
So if I want this to not deflect or to deflect a minimal amount, what can I do? So how do I design a center drill so that my little divot will be in the right place?
If you have a larger radius over length ratio, then this will guarantee less,
So if I
less
make
deflection.
my radius to length ratio be big, right? I want length to be a small number and radius to be a big number relatively. That will make my drill more stiff from bending. The other thing I could do is I could get a stiffer material, right? The other thing I could do that would have the same impact as a stiffer material is I could get a lower cutting force. Do you ever notice that if you start the drill slower, it walks out less.
Mm-hmm.
What you've done there is you've reduced that cutting force by changing the velocity of the tool moving through the workpiece material, of the cutting edge of the tool, right? That tip. Then once it gets going, you can pull the trigger. I think the inventor of variable speed drills deserves a pat on the back. All right, so we want the hole to go where we want it, but that's a manufacturing question. Why do I bring this up when we talk about design for manufacturability?
Well, part of the thing could just have to do with like where the holes need to be, because we want to reduce the radius as far as accessibility, or the length, sorry, as far as accessibility goes.
Okay, so if we needed to put holes here in our piece, and we had a big feature that was tall next to it, not really good at drawing in 3 dimensions, but you get the idea, right? You might then have to have a really long drill in order to make this hole. I might not be able to use a short stubby drill because I may not be able to get the spindle close to this without crashing into the big tall thing next to it. It actually comes up here in this part. You can see it. This hole right here is next to this wall right here. If I wanted to use a short stubby drill to make a spot drill for that hole, I would have to get the spindle close down here, and the tool holder could run into this little rail part. How do I fix that manufacturing problem on this part?
Flip it over.
I drill the holes from this side. That's one way to fix that problem. So if I can't use a short stubby drill, my options are to fix force and to fix elastic modulus. This is one of the reasons you don't know this, but in the lathe, when we make the cylinders, there's a drilled hole that goes all the way through the part that's a pretty small hole. So how much do you think one of these drills costs?
A lot.
But no.
Or wait, the drill or the drill bit or like the...
Yeah, that's called the drill.
At least 3.
Depends if you're buying them in bulk.
I get 2 drills here that are about the same size as each other. I knew I had these. So these 2 drills are about the same size as each other. This one cost about 94 cents. This one cost about $50. Why the difference in price?
Material.
This one is made out of silicon carbide and it's coated. This
Marketing.
one is made out of tool steel and it's not coated. Actually, this one's made out of drill rod, even cheaper than tool steel. This one's really cool too. You probably can't, it won't focus that close in. But if it would focus that close in, you would see that there are 2 little holes in the tip of the drill. And there are 2 little holes in the other end of the drill. And that's to let coolant come out the tip of the drill. So you spray coolant down in the bottom of the hole while it's drilling to push the chips back up out of the hole. This drill is made especially for making holes with a large length to diameter ratio. If you need to make a hole with a large length to diameter ratio, you risk any little misalignment. Even with a spot drill, you could have a little bit of misalignment, right? Any misalignment, the deeper the hole goes, and the skinnier the hole is going to risk breaking the drill or having the hole come out in the wrong place. We use a drill like this, a carbide drill like this, in the cylinder operation to make that long hole that comes out the other side, because when we were using a drill like this to make that hole, they never came out in the center of the part. because the drill would always deflect and go a different direction inside there. Even though the depth of the drilling operation was short, the length of the tool in order to reach the bottom of the hole was long. So, so when you have a long, deep hole like that, if functionally you need that, then it's okay to have it. But if you don't need it, then you should use a larger diameter hole so that you get a smaller length to diameter ratio. What if, and this happens, I see this all the time in parts that we do in the lab here. We'll have a part that looks like this, a cylindrical part, looks like this. It has a hole in the center, and the hole needs to come all the way down here. And the diameter of the hole needs to be 0.060 inches. 60 thousandths. That's a very common diameter for a hole like this in a part that we make here. Oh, and this length is like 1.5 inches. Now, if you want to know what's a good rule of thumb for a length to diameter ratio for a drilled hole, you could ask Google. Drilled hole drilled hole length to diameter. How about rule of thumb? Here's a page. Let me see. Can I do screen share? Quick. Share the screen. Which one? Oh, 3. Oh, well, that's not what I asked for, Google. This is what I get for, no. All right. Try 4 or 5. I thought I was going to look up and there was going to be a cool picture and it was going to show us everything, but that's what I get for not planning in advance my screen shares. Oh, people were posting in the chat. It was a link to where the equation was. Okay. How do I solve this problem? I mean, I could get a fancy, expensive carbide drill, but I can do this without the fancy, expensive carbide drill.
By like doing multiple.
What's the first thing I ask, especially when it's a WPI student who wants to drill a hole like this? What's the first thing I ask them?
Why do you need to drill a hole like that?
Why do you need that hole? And they tell me because they're going to take a thermocouple wire that needs a 60 thousandths diameter hole so that the tip of the thermocouple will be touching the material so that it will transmit the heat into the thermocouple wire and they can accurately measure the temperature of their sample as they do some sort of experiment that involves heating and cooling. This is the part they care about measuring. They need it to be 60 thousandths here. They don't need this to be 60 thousandths. We can drill a bigger hole.
You're going to break your bit drilling it that long.
And then a smaller hole down here. So there are some tricks. You will need a special long, extra long drill bit to make this little bit of it. You want to make sure that the drill that you use here to get access to the little one has the same tip angle as the drill that you use to make this one. When you do that, that skinny drill is going to come down here and it's going to get guided by the bottom of this into the center again. And you don't have to go very far at the small diameter. So even if this one does walk out a little bit, it won't walk out enough that it will break the drill before you get deep enough so that you can get a 1/4 inch of that thermocouple into the part. So that is a solution to when you needed a small hole. This could be a through hole too. Sometimes you're gonna have a fairly thick part like this. You're gonna have a fairly small threaded hole over here with threads in it to screw something down. Maybe you're gonna mount something to it over here. And you've got a screw that's gonna go through that to hold this together. And for whatever reason, you can't access the location where this hole is gonna be drilled from this side. So you have to drill it from this side. If you try to drill a long skinny hole and then put threads all the way through it in order to get this fastener to engage, you're going to have the same problem that we had over here. But you could drill a bigger hole over here, come in with the smaller drill and tap to put the threads right here, and then still be able to put your fastener in from the other side. So another occasion where you want to leave access for the tooling, it's the same idea as if you had a large feature next to where you need the hole to be, so that you can leave access for the tooling to come in from the other side, things like that. All right, so we don't want to have deep holes. The same goes for deep pockets. You don't want to have to do a pocketing operation or a side milling operation that goes very far into the material for the same deflection reasons. So our end mills, even our carbide end mills, deflect out as we're doing cutting. They deflect out from the cutting force. The cutting force is going to be applied where we're doing the cut. And so the longer that end mill is, the more deflection you're going to get. Actually, there's these pockets that you see in here. Those were actually pretty difficult to make because in order to fit the tool in there, it had to have a long reach. And when you have a long reach, if you could see close up, you'd see there's some pretty ugly surface finish on the edges of those pockets. They were only there to remove material to make the part lighter, so it wasn't a big deal. And Paul didn't care. He painted the thing anyway. What else? Design for machinability. I think we've covered most of the high points, the stuff that's going to get you in trouble when you do your MQP. Remember, use the machinery's handbook when you need to figure out what size the hole needs to be to get the clearance or the slip fit or the press fit that you're trying to do. And yeah, all right, so we're about halfway done. Why, we talked about this before, but why again do engineers measure? Why do engineers measure things?
It usually works out a lot better than guessing.
But what's the purpose of the measurement?
Repeatability.
Well, it will tell us if we have repeatability. It'll tell us if we have accuracy. It'll tell us if we've made the part the size that we intended to make the part.
It saves money.
It could save money depending on. So if shipping right. Why do scientists measure things?
So measuring allows you to quantify.
It allows
So
you
you're
to
able to
quantify something, It allows you to understand something. And so scientists typically will measure things because they're trying to figure something out. They're trying to understand how it happened, right? Engineers, now, sometimes engineers do it for that reason too, but then they're being scientists, right? They're doing science when they're trying to figure something out. Engineers measure things typically because they're trying to control the process. So manufacturing engineers especially. We measure things because we're trying to control a process. We're trying to make sure that we make good parts that we can ship to our customer. Whether we're doing it for a final inspection, so we do that final check before we put the part in the box and ship it, or if we're doing it to control our manufacturing process to make sure that we never make any bad parts. Engineers are typically measuring things in order to make sure that the process is controlled. What's the difference between accuracy and precision?
Accuracy would be like a cluster grouping that's really close to something, or to each other, and then precision would be like if you're aiming at a target, for example, like precision would be getting a bullet through the middle of the target. Accuracy would be.
Anybody ever played darts?
Yeah.
Darts, so you throw darts at a dartboard? Anybody really good at it? Nope. I used to be really good at darts. Because when I was a little kid, my father's good friend was a darts champion. I'm pretty sure to become a darts champion, you spend a lot of time in bars. Because dartboards tend to be in bars and dart tournaments tend to be at bars. So maybe this guy drank a lot. I was too little, I didn't notice. But so when you throw the darts, you're aiming at a spot on the dartboard, right? You're aiming at a spot on the dartboard when you throw the darts? Usually?
Yeah.
Yeah, okay. Just making sure that you guys can still hear me. So if you get all of the darts on the target, stop my screen share for just a second. If you get, so if here's the target. Let's say the target has a bullseye, then there's another circle around the bullseye, and then typical dartboard will have different regions coming out from that bullseye. We're kind of zoomed in the center of the dartboard here. You guys can all picture this though, right? So if we're shooting, and they call the center of the dartboard the cork. So if we're shooting for the cork there, if I get one here, and one here, did I score any points? If this is the one I needed to hit to score the points.
No, but you were precise.
I was very precise, but I was not very accurate. To be accurate, so if I got one here, and one here, at least this one was accurate, but they were not very precise. So precision is the closeness of the in my example case, it was the closeness of the darts to each other. And so if you're at the bar playing darts, when you get it very precise like that, your buddy will hand you your beer back and they'll say, nice grouping. And nice grouping is a good way to say, hey, you're pointed at the wrong direction. So if we have precision like this over here, can we fix the problem?
Yes.
Yes.
Quite easily.
Yep. We probably just need to fix the aiming mechanism, right? So you see in the movies with the snipers and their rifle with the scope, right? They shoot at something and they see where the bullet goes, and then they turn some knobs on the scope, and then they shoot the next time and they hit the center of the target or whatever they're shooting at, right? So if you have precision and not accuracy, or if you have precision, but you're not accurate, you can fix that problem. If you don't have accuracy, can you fix that problem?
Yes, but it will take longer.
How are you going to fix the lack of accuracy problem?
By changing one of many variables.
Let's take, for example, throwing darts. If I was going to say the sniper, but let's do throwing darts instead. It's a little bit less violent. If we're trying to throw darts to hit the center of the thing, and we're not accurate, we don't have any precision, what do we have to do if we want to hit the center of the thing?
Throw more darts. Get better at throwing darts.
Fine, right?
Yeah.
So if you have a lack of accuracy, and so this works the same with measurement devices. So if I'm trying to measure a dimension and my measurement device is not accurate, typically if we have that kind of a problem, and it's like the picture shows here, is because we lack resolution in our measurement device. So it's not capable of measuring a number as fine as the number that we want. So if I keep measuring and I make a lot of measurements and then I take the average value of all those measurements, it's probably in the center of those four right there. If I average all of these together, I'm still not accurate. But if I average these together, I'm somewhere in the center. So one way that you can fix a lack of accuracy is by taking a whole slew of measurements and getting the average. And so what keeps them, both of these conditions, we have measurement uncertainty. We're not sure what the true value is, but with this problem, we have random errors, and we can fix random errors by measuring a lot and finding an average. With this, we don't have random errors, we have specific errors, and we have to actually physically fix those in the system in order to get it to be accurate. So yeah, the ISO standard will define accuracy as closeness to the true value and precision as closeness to the other measured values. So in engineering, especially manufacturing engineering, what is it that we typically measure?
We will measure the final machine part in reference to
what are the parameters we measure?
Like where the location of the holes are, diameter of the holes.
So the location of the hole relative to something. So we're measuring length, right? So we're measuring the location of a hole relative to something else, relative to the edge of the part, relative to another hole. We've measured a length. What else do we measure in manufacturing?
Features?
What do we measure about the features?
Depth or
Depth is the same thing as length. It's a distance.
yeah, that's true. You can measure a radius or a diameter.
A radius or a diameter is really a series of lengths, right? I'm gonna put radius, but you can find it by measuring length. Radius. Because there's some specific ways to measure radius. What else are we going to measure in manufacturing?
Machine time.
So we might measure time. There's no significance in the color change. It's just the marker I happen to grab. What else might we measure?
Mass.
So he said mass. What else might we measure?
Stress and strain.
Stress and strain. How do we measure stress and strain?
by trying to break the part.
We measure strain by measuring length, right? Because strain is the change in length when a force is applied. What's stress? It's force over area, right? Area is length, but force is an independent thing. So we need to measure force. How can we measure force? Simply. We can put a mass on a string and assume that we know what the acceleration due to gravity is. But we can measure force. Okay. So as manufacturing engineers, most often we measure length. What's the other way to measure force indirectly? Manufacturing engineers do this all the time.
Pressure.
So pressure is just the same thing here, right? Force over area. I know that because the units are pounds per square inch. What else? What else could we measure? You're thinking of, so this is a physical thing on the part. This is a physical thing on the part. This is about controlling the process and understanding rates. This is a physical thing on the part. This is about understanding the process.
Hardness of a finished part.
So hardness, to measure hardness, we measure force and we measure length or area.
Temperature.
Then we do some math. We could measure temperature. In fact, if we want our length measurements to have any real value, one of the things that can cause that accuracy to be off is the temperature changing between length measurements. Because most materials that we use in engineering have fairly high thermal expansion coefficients. So they move a lot with changes in temperature. So the other thing that I think we've missed here is that we can get force by measuring power and knowing velocity, right? And we know the velocity because we decided what it was going to be, but velocity is just length and time. So how do we measure power? Any double E's in the group?
Is it IR squared?
I think somebody said it, but it was two people talking.
I think it's IR squared.
I think it's something like that too, right? What's I?
Current.
Current. What's R?
Resistance.
Is that correct?
I think the R is squared too. Oh, well, yeah.
We certainly have to measure current to know power. We know power, and so isn't it volts equals I R something?
Yeah, it's just volts
I believe
equals IR.
power should be the current squared times resistance.
Oh, squared. Right, so we can measure power because we can measure current. And those are pretty much the things manufacturing engineers measure. I suppose we measure N. What's N in this case?
Spindle speed?
No. It's number. We count things, right? We count the number of parts that we made. We count the number of people that came to work. we count the number of pieces of stock material that we have left. And so counting is a measurement too, I suppose. All right. Those are things we measure. How do you measure radius?
You measure the respective diameter of the part that you want to know the radius for and divide that number by 2.
Okay. So if you have a round part, you can measure the diameter with some sort of diameter gauge, right? Our calipers can do it. We use a micrometer. We can measure that diameter. We can actually wrap a string around it, measure the circumference by finding the length of that string and calculate the diameter back, right? What if we don't have the whole thing? What if we have more room on our whiteboard? What if we have a part that looks like this? And that radius is a critical dimension. And this is material. This is space. How do we measure that radius?
By using like 2 different arcs.
We take stuff that we know the radius of, and we see if it fits in there. So it's called a radius gauge. And you can do it for concave shapes or convex shapes. You can do it, the radius gauge. How else could I measure this radius if I didn't have a radius gauge? If I had a reference surface that I could cantilever out over here, I could measure the depth and 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 the depth, and I could put it on a graph and plot it. I can calculate the radius. All right, I think we're running out of time. I'll stick around for a few more minutes if people have more questions, but you guys are free to go.